Okay, guys, welcome to the second lesson for stoichiometry. This one, we're going to do a little bit more complex problems than we did before, not just simply using a multimole ratio, but using the multimole ratio to find um, mass or volume or whatever. So let's see here. Okay, so same starting point. You guys are going to need a calculator, your notes, and a pencil. I'm going to try to get you to practice a little more during this one than I did last time, but we'll see how that goes. So for lesson 2, our objective here is to perform some little bit more difficult stoichiometric calculations involving mass, particles, and volume. I'll take you through them, but essentially we're just using the multimole ratio and knowledge from previous units to solve. So here we go. When we're actually measuring things in lab, you can't just go over to a balance and measure a certain amount of moles of a substance. That's not possible. What you use on a balance is going to be mass. So mass is something tangible. So you can go measure the mass of something. But to know how much of one substance you need relative to another substance, you need your multimole ratio from your balanced equation. So we're going to use molar mass, at least in laboratory situations, to actually calculate what we need. We could do the same thing with volume if we had a way to measure volume. But yeah, you can't just measure moles using a graduated cylinder or a balance. Experimentally, that is not possible. All right, so steps to a stoichiometry problem, and I'm just going to kind of fly through this. I have found that it's better for you guys to see than it is for me to read. But okay, first thing you do is you write a balanced equation. You identify what your given and your wants are, your knowns and your unknowns. You're going to have to convert whatever mass it is that you're given to moles so you can use your multimole ratio. You're going to convert the moles of the first substance. Here's the important part. You're going to convert your moles of your first substance to moles of the second substance by using that multimole ratio. And then you are going to convert the moles to whatever substance it is that you're looking for. If it were a mass problem like we're going to do first, you would change from grams to grams or kilograms to kilograms by going through that multimole ratio. You are free to use your mole roadmap while you're practicing these, but again, that won't be something that's on your exam, not the mole roadmap. So let's go do the first example. So this one says, calculate the number of grams of solid sodium oxide that would be produced when 115 grams of solid sodium reacted with excess O2. Now this excess word here means that you just have plenty of O2. We'll get to what it means when we're limiting how much we can make, but for right now, we're just going to do it with excess. All right, so we need to write a reaction first. So it says the amount of sodium oxide that's produced. So what we're going to produce is going to be sodium oxide. So I put that together by my charges or by its charges. Sodium is a +1, oxygen is a -2, so it's Na2O. It's solid sodium oxide produced. Well, that's produced from sodium reacting with, it said, excess oxygen. This is not a balanced equation. To balance my oxygens, I'll put a 2 here, and then I will put a 4 in front of the sodium, and now the equation is balanced. Now they're giving me produced when 115 grams of solid sodium. So this is 115 grams of solid sodium. And what I'm looking for is how much in grams of the sodium oxide is produced. Okay, so what I'm starting with here is grams, and what I end with is grams. The only way that I can change using my balanced equation from one substance to another substance, in this case a reactant to a product, I'll need to change it to moles first and then use my mole-mole ratio. So what I'm going to do is I'm going to take my 115 grams of sodium that I'm given. I'm going to draw a line, and then I'm going to draw another line. I can change from grams of sodium to moles of sodium by using my molar mass of sodium, or atomic mass, if you like, from the periodic table. If I look up sodium's mass, it is 22.99, writing smallly, sorry about that. 22.99 grams of sodium is 1 mole of sodium. At this point, I will have converted it to moles. So I'm going to draw another line, and I am going to convert moles of sodium to what I'm looking for, which in this case, 4 to 2, I'm changing to moles of sodium oxide. There are 2 moles of sodium oxide for every 4 moles of sodium from my balanced equation. I'm going to continue my line, draw another line. And what I want to end up with is grams. And at this point, I would have moles of sodium oxide. So what I'm going to do is convert from moles of sodium oxide to grams of sodium oxide. And if I add 2 times 22.99 and then 16.00 for my oxygens, I get 61.98 grams of sodium oxide, Na2O. And I would get my answer. If I multiply across the top, multiply across the bottom, divide the 2, I end up with 155 grams of sodium oxide produced. Okay, pretty straightforward. The only thing that is new here in solving for this mass-mass problem is the mole-to-mole ratio. Changing from grams to moles, that's just molar mass. We've done this in the past. Changing from moles back to grams for the sodium oxide, once again, just using your molar mass. So let's check my work, make sure I did this correctly. Yeah, there we go. And like the arrow says up there at the top, the excess just means that you have more than enough. So in other words, if you're making hamburgers and you have 100 buns and you only need to make 5 hamburgers, you have extra hamburger buns. In this case, we have a limited amount of sodium and we have plenty of oxygen for it to react with. So we're not worried about how much of the other substance we have. That's the reason for the word excess. We'll deal more with that in the third lesson. Okay. So here's another one. It says how many grams of oxygen are required to burn C2H4 or 13 grams of ethine or acetylene. Okay, so how many grams of oxygen are required to burn? So this is a combustion problem. My reactant is going to be C2H2. My other reactant in a combustion problem is always oxygen. My products of a combustion reaction are always CO2 and H2O. Okay. So what I'm going to do is balance my equation first. I am going to need, let's see here. I am going to need 2 moles of carbon on both sides. So I'm going to put a 2 in front of my carbon dioxide. I also need 2 moles of hydrogen, which I already have. If I look on my product side, I've got 5 moles of oxygen. What do you multiply times 2 to get 5? Half of 5, or 5 halves. I could then multiply all the way through my equation by 2. So I would get a 2 in front here. I would get a 5 here. This would become a 4, and then moles of water would be 2. I'll clean that up by putting a 4 here, and I'll clean it up by getting rid of this nonsense and putting an actual 5 here. And so now it is balanced. My given and my want, what I'm given is 13.0 grams of the C2H2, the acetylene, the ethine. And what I'm looking for is how much oxygen is necessary to react with it. Okay. So, how about you? I'll tell you what, I'll set you up here. You need 13 grams of the acetylene to start with. But what you want to end up with is grams of oxygen. How about you hit pause, go ahead and set this up, use your calculator, go get your answer, and I'll kind of whip through it and show you after you give it a shot, okay? Please press pause and give it a shot, use your calculator. Okay, so let's assume that you did it, right? So I would need the molar mass of acetylene, which going and calculating is 26.04 grams of C2H2. That would give me a mole of C2H2. And then I need my mole-to-mole ratio from my equation, 2 moles of C2H2 for every 5 moles. That's what I'm looking for of O2. And the molar mass of oxygen gas is 32.00. I would get my answer. I got 39.9 grams of oxygen gas. Hopefully you got the same thing. If I scroll up and check my work, let's see, checking my work, yay, 39.9 grams. So set up the same way. Hope you guys did that one correctly. Let's try another one. So that's mass, right? So changing from mass of one substance to mass of another substance, regardless of whether they're reactants or products. So here's another one. How many grams of carbon dioxide and grams of water are produced when that 13 grams of C2H2 reacts with excess oxygen? So in this case, if I go back up, it's the same problem, right? So I'm just doing a part B of this problem, solving for the CO2 and the H2O. But I'm going to do two little calculations to find out how much of each of those are produced. So I'll have two different equations. Now, I could use the answer from one equation to solve for the other equation, but I find it a little bit easier to kind of do them both the same way. So 13 grams of C2H2. And in this case, I'm getting ahead of myself, aren't I? I'm starting with 13 grams, my bad. And what I'm solving for is grams of CO2, and I'm solving for grams of H2O. So I would set these up as two different problems, 13.0 grams of C2H2. And I'm going to go solve for grams of the water. I'll pause. You can hit pause and go and try this one as well. You should get two separate answers for this. I'll give it a shot. So assuming you guys did this, I'm going to scroll up and just show you the work. But yes, you would need the molar mass of C2H2, which we previously calculated on the other problem. And then you would need the molar mass of CO2 and the molar mass of water to solve the other two problems. So they would look like these two here. So I have the 26.04 moles, or 26.04 grams of the acetylene, a 4:2 ratio from the balanced equation. Remember? My 4:2 ratio is coming from here, this 4 and this 2. And the 2:2 ratio down here at the bottom is coming from my 2 moles of acetylene and my 2 moles of water. The rest of it is just the molar masses. So check your work, 43.9 grams of CO2 and 9 grams of water should have been your answers. So obeying the law of conservation of mass, if you looked at both of them and you added them up, so if I add my products together, so my two products there were 43.9 grams of CO2, my 43.9 grams of CO2 and my 9 grams of water. If you sum those two together, you get 52.9 grams. If I look my beginning, the 39.9 grams of oxygen and the 13 grams of C2H2, they are the same. So by adding the two together of the reactants and adding the two together of the products, I can see that the law of conservation of mass holds true. And so, yes, this does obey the law of conservation of mass. Here's another one for you. So how many grams of tin 2 fluoride or stannous fluoride can be made with reacting 7.42 molecules, reacting 7.42 times 10 to the 24 molecules of HF, hydrofluoric acid, with the tin? So the first thing we would need to do is write our balanced equation. So I'm going to go ahead and do that for you. So how many grams of those are made with reacting it with tin? So tin's formula is SN. I am reacting with it hydrofluoric acid. And I am producing stannous fluoride as a result. There is something else that's going to be made as a product. The hydrogen would be given off. Please don't forget that hydrogen is diatomic, so you'll need to write that as H2. To balance the equation, I'll go put a 2 in front of the hydrofluoric acid, and we've got a balanced equation. My given in this case is not mass, so this is not a mass problem. We are looking for how many grams, though, of the stannous fluoride. So over here, I'm going to need to find that number of grams. And in this case, I'm actually given 7.42 times 10 to the 24th molecules of this substance as my given. So when I start this equation, I'm going to start with 7.42 times 10 to the 24 molecules of HF. And I'm going to change from HF to the stannous fluoride. So in order to change from molecules to moles so that I could use my coefficients and my mole-to-mole ratio, I'm going to use Avogadro's number, 6.02 times 10 to the 23rd. Kind of run out of room on this one, I think. Molecules of HF. That will give me 1 mole of my hydrofluoric acid. My coefficient of my hydrofluoric acid is 2 moles of HF for every 1 mole of my stannous fluoride. And then using the molar mass, because I'm asked for how many grams in this case, 1 mole of the SNF2. Calculating its molar mass, it gives you 156.71. Oh, goodness. Well, those things do happen, don't they? Well, let's end that. Sorry, guys, my daughter's calling me. Okay, 156.71 grams of the SNF2. And so if I go ahead and calculate, I get 966 grams of SNF2 as my answer. Okay, so this would be going from representative particles through our mole roadmap all the way to mass of our product. Now our product in this case. Okay, cool. Let's check my work. So going to 960, yay, 966, yay, look at that. Okay, we'll do part B on this one. So how many liters of hydrogen at STP were produced by reacting 23.4 grams of tin with HF? It's the same equation that we had before. Hopefully we bounced it right the first time. But what we're looking for here is how many liters of hydrogen gas. So here I'm looking for liters are produced by reacting 23.4 grams with HF. Now they didn't say that it was excess HF, but we'll make that assumption. So the 23.4 would be our starting point here to solve for liters. Why don't you guys go ahead and do this one again on your own, give it a shot. You can hit pause now. I'll go ahead and work through it, but hit pause and then come back and see how to do it. Okay, so hopefully you have an answer. I took my 23.4 grams of tin using the molar mass off the periodic table for tin, or the atomic mass. I did 118.71 grams of tin is 1 mole. From my balanced equation, there is a 1 in front of tin and a 1 in front of the hydrogen. So my mole ratio is 1 to 1. So 1 mole of tin for every 1 mole of hydrogen gas. They're asking for liters this time. How many liters of hydrogen? So I'm going to use my 22.4 liters of gas at 1 mole, or 22.4 liters of gas is 1 mole at STP. So 1 mole of hydrogen gas would be 22.4 liters of hydrogen gas. That's a terrible really. 22.4. I solve and I got 4.42 liters of hydrogen gas as my result. So maybe you think that these, or thought that these were more complex than the others. Really all we're doing is adding in stuff from our mole unit, our conversion factors, in order to solve these. But essentially, once again, the new thing here really is just the mole to mole ratio. So another one, if you go from volume to volume, we can't, well, let's go ahead and scroll up and check my work there. There we go. It's correct. I could also have volume calculations. Here it says how many liters of HF are needed to produce 14.2 liters of hydrogen. So here what I'm looking for is how many of these liters to produce 14.2 liters of the hydrogen gas. Again, this is stuff you guys have got to practice. This one's pretty easy. It's 22.4 and 22.4. But go ahead and set it up, give it a shot, and I'll show you the work in a second. Okay, so let's see what you did. Hopefully you started with 14.2 liters of hydrogen gas. To change and use my mole to mole ratio, I would need 22.4 liters of hydrogen gas is 1 mole of hydrogen gas. And for every 1 mole off our balanced equation here, 1 mole of hydrogen is 2 moles of the hydrofluoric acid. It asked for how many liters here, how many liters of HF. So in order to do this, I would do 1 mole of HF is 22.4 liters of HF. Terrible liters. And my answer is 28.4 liters of HF. Now, many of you are noticing, I hope, that you've got 22.4 and 22.4 here. Clip. My AP kids, I would tell them, if you're going from liters to liters at STP, all you really need is a mole to mole ratio. Liters and moles are directly related. And so here, the 22.4 is going to be the same in top and bottom. All you really needed to do is multiply it by 2. You could certainly do the work and won't take you very long. You guys will have plenty of time on your exam, but you could just use your mole to mole ratio. So scrolling down and checking my work, there you go. I'll take care of C. So just one more. This one here, Volume, we already did a volume equation. Let's just go do one last one where we've got 80 liters produced. Okay. So again, you could pause and try this one. I'll go ahead and work through it. Hit pause, come back to me. Okay, so what I was given here is my balanced equation is the same. I'm given 80 liters of hydrofluoric acid, so this would be 80.0 liters here at STP. That's important actually, so we can use our 22.4. So 80.0 liters, and what I'm asked for is molecules of hydrogen. So I'm looking for molecules. I don't know how many molecules of hydrogen I need. So I'm going to start with my 80. Gosh, I should start further over, huh? That's not 80, 80.0 liters of HF. To change to moles, it's the only way that I'm going to be able to change from HF to hydrogen is my mole to mole ratio. I need to change this using 22.4 liters of HF, or 1 mole of HF. I can use my balanced equation. There's a coefficient of 2 for my hydrofluoric acid and a coefficient of 1 for my hydrogen gas. And then 1 mole of hydrogen here did not ask for liters. It asked for moles, or molecules rather. So I'm going to use Avogadro's number, 6.02 times 10 to the 23rd. I'll abbreviate molecules of hydrogen. The answer I got, hopefully the same as yours, 1.08 times 10 to the 24 molecules. Since I've got some room, I'll just write it all out. Molecules of hydrogen. Okay. Maybe you think these are complex, maybe you don't think they're complex, but these are what we are considering the more complex of the two. So a little bit more difficult level of questions for stoichiometry. So that concludes lesson 2. The last thing that we have to do, checking my work, there we go. The last thing that we have to cover is going to be limiting reagent and some percent yield calculations. And so I'll show you how to do those in lesson 3. I think Aiken left this here for you. Chemistry's fun, right? I'll see you guys in the next lesson.